We are arriving at the last part in the chapter about the lithosphere, and we will quickly present the types of rock and the rock cycle that you will see in details in the second year, next year. So the minerals form rocks, and rocks are separated into three main types: eruptive or magmatic rocks that crystallize from magma. And here we have two types of magmatic rocks: volcanic or extrusive, which are the rocks that cool rapidly outside, okay, and plutonic or intrusive rocks, which cool down slowly inside the globe. Now we also have sedimentary rocks that are formed on the surface of Earth and are very abundant on the surface of Earth, and they come from either the precipitation of dissolved elements in water or by the accumulation of debris that come from the erosion of continents and are transported by streams and then submitted to cementation and to processes that transform these sediments into sedimentary rocks. Metamorphic rocks are formed by the transformation of either sedimentary rocks or eruptive rocks in depth under the effect of temperature and pressure. So we have the crystallization of new minerals in these types of rocks. Now here in this graphic you have a recap, and in this slide also you have the explanation for the graphic. You can clearly see that it is a cycle. It all starts with magma, which is fused rocks, and the crystallization into igneous rocks, and then these igneous rocks can undergo erosion and form sediments, and these sediments will then undergo diagenesis to form sedimentary rocks. These sedimentary rocks can undergo metamorphism as well as igneous rocks and give us metamorphic rocks. Now, please note that metamorphic rocks can also erode and give us sediments, and sedimentary rocks as well may be eroded by wind and water and give us back sediments. All of these rocks can undergo fusion and give back magma. Okay? So you can find what we talked about, these phases, in this slide. What about the deformation of rocks? So when subjected to stress, the Earth's crust is deformed. The deformation may be plastic, such as a ball of modeling clay when it is crushed, or brittle, such as breaking glass. So the parameters that are to be considered when applying a stress-strain concept to material of the Earth's crust are the following: pressure, which of course increases in depth; temperature, which also increases in depth; time; and finally the composition of the rock and the nature of the rock. We have some rocks that are brittle by nature, like the limestones that are very rich in Lebanon, or others that are more plastic, like clay rocks. Okay, now the formation may be due to different types of constraints. You have tension, where the material is being stretched. Okay, you have compression, where as you can see here, the material is crushed, compressed, and we have shear stresses that push a rock or two pieces of rocks in two opposite directions, causing breakage or a change of shape. Now, the results of these constraints may be faults, for example, Now, folds are formed by slow and continuous movements. They are produced by compression forces here and here. Compression will cause these rocks to fold. Now, we can see more clearly folds when we have a layered rock. It is more easy to see the folds. Now, the fold may have this shape or this shape. In this case, in the first case, it's called an anticline. You can remember that because it has the shape of an A. And in the second case, it's a syncline. There are other examples, but these are two examples of folding. For plastic deformation of rock to occur, there's a number of conditions to be met. First, the rock must be able to deform under pressure and heat, and the pressure must not exceed the rock's internal force. And the pressure must not exceed the rock's internal force. Otherwise, it will break, and this will be faulting this time. So this is a real picture of a real anticline and a syncline. And now we will be talking about faults. The process is called faulting, and it is due to stress of tension, compression, or shearing. Okay, now the two compartments on either side of the fault can move, and the block above the fault plane, so here you have it, the fault plane, the block that is above the fault plane, like that, is called the hanging wall, and the block below the fault plane is called the footwall. Now, in a normal fault, like we have here, okay, the hanging wall slides downwards. It's a result of tension. You can see the arrows here. Tension, which is stretching, causes a normal fault, and it causes this hanging wall to slide downwards. Now, in the case of a reversed fault, look at the arrows. You can see that it is a result of compression, and you can see that the footwall slides on the fault plane. Now, in a strike-slip fault, like you can see here, there is horizontal sliding of the two blocks with respect to each other. Now, regarding the transformation of our crust, there is also, we talked about erosion. So, erosion is caused by runoff, by ice and wind, so basically by all the fluids that exist on our planet. And these winds and precipitation flatten the continental landform towards a basic profile that is the sea level. Okay, you can see here we have a mountain range and we have erosion, and we have later on some particles that go to the ocean. Okay, these are the sediments. They came from the erosion of this mountain on the continent. Okay, so what happens after the erosion is done? There is a process called isostatic adjustment. Actually, the removal of a quantity of material requires a rebalancing of the mass by the rise of the continental lithosphere. So we have a push upward of that mass that was much more massive in the first picture here, as you can see, and it caused the deformation of the asthenosphere. So as the mass becomes lighter, the asthenosphere comes up again. As you can see here, we have a rebalancing. And the sediments that came from the continent to the ocean cause the oceanic crust to become heavier and to undergo subsidence and go down. Okay, the last phase is when, as you can see, the mountains are almost totally flattened and they join the sea level. Okay, this phase is called the peneplain. Now, two more slides just to give you an idea about the fossil fuel. Um, how is coal formed and how is oil and gas formed? Uh, First of all, you have to know that the coal and the oil and the gas we are using are called fossil fuel. They are not renewable energies, because by the time we have used these fuels, there will be no time for a new fossil fuel to form. They were formed millions of years ago, and the process is very, very, very slow. So we are using up this fossil fuel, and soon we will be out of fossil fuel. Okay. Now, how is coal formed? In a few words, it's made of terrestrial plants that accumulate in anoxic areas, which are swamps, for example. Okay, in swamps we have a lack of oxygen and lots of vegetations that grow. Now, the stacking and the burial of these material under the sediments will cause volatile materials such as oxygen, hydrogen, and nitrogen to be released. And what remains is the carbon that is concentrated with time and with more burial. As you can see in the picture here, we have a swamp. At 50% carbon, the material is called peat. Now, you have more burial, and at 70% carbon, it's called lignite. At 85% carbon, more burial, it's called bitumen, and at 83% carbon, it's called anthracite, which is coal. Now, coal was heavily used since the Industrial Revolution and is still used in some countries, mainly in China, for thermal power plants and steel plants. Now, oil and gases, on the other hand, are formed primarily from phytoplankton, also in oxygen-poor waters, where we have a quick and a rapid burial of the material in the presence of fine clay particles. Actually, what happens is that the material is trapped in the clay particles, and there is little free oxygen that may be present in such conditions. Now, this oxygen is rapidly consumed by oxidation of a small part of the organic matter, and then we have anoxic conditions. Now, the organic matter composed of CHO and N is then protected from oxidation, as we said, by the clay, but you know also that there is some anaerobic bacteria that use oxygen, nitrogen for their metabolism. So this is called biochemical degradation. So oxygen and nitrogen are subtracted from this initial organic material, and we have what we call kerogen. Now, kerogen is hydrogen and carbon. So it undergoes thermal degradation and gives us some gas. The first molecules that are formed are methane, CH4, and also with higher degradation, hydrocarbon molecules become more complex, and they will give us also oil. Okay, and we will have also some residues of carbon. So this is it for this chapter.